All right, so let's just review real quickly what we were looking at yesterday. And also look here at an example of the type that we introduced the concept for yesterday. But we didn't necessarily do an example. Here we have the area of the region between the graphs. So between the graphs, enclosed by the graphs, contained within the graphs, all those things. We're needing to look at intersections, all right? So here we have f of x is 3x cubed minus x squared minus 10x, and g of x is negative x squared plus 2x. So the first thing, I know it's on the graph here, but remember the first thing we've got to do is find those intersections. So you're setting the f of x equal to the g of x, 3x cubed minus x squared minus 10x equals a negative x squared plus 2x. And since it's a polynomial, we get it equal to 0. And this one's kind of nice because we've got a 3x cubed. The x squareds will cancel, and we have a minus 12x. And that all equals 0. So we factor this one out. 3x is x squared minus 4 times x squared minus 4. So x has to be 0 or plus or minus 2. So at this point, we know we're going to be taking an integral from negative 2 to 0. And then we're going to add the integral from 0 to positive 2. The question is, which one is bigger in each of those intervals? Okay? Now, from the graph we can tell easily, but you won't necessarily be given the graph. So if you just plug something in, like you plug in a negative 1, if I plug in a negative 1 in f of x, I get negative 3 minus 1 is negative 4 plus 10 is 6. If I plug in a negative 1 here, I have a negative 1 minus 2, negative 3. So f is bigger. So I have the 3x cubed minus x squared minus 10x minus the x squared plus 2x. dx. Okay? You could also then plug in a 1. 3 minus 1 minus 10 is negative 8. Negative 1 plus 2 is 1, so the g is bigger. Okay? Remember, another way you can handle this is since you're setting it up, you could just subtract them in whichever order you want and take the absolute value. Okay, just make it be positive.
Shouldn't there be a negative on that x squared, the first one?
There?
Yeah.
Yeah,
So
thank
you
you.
can tell which one's bigger by plugging in 1?
Plug in something in the interval from 0 to 2 in this case.
Okay.
Yeah. So then minus 3x cubed minus x squared minus 10x dx. And then it's just a matter of finding those two integrals. Okay? Of course, simplify first. Combine like terms. It does make it easier. Okay? Here, when you combine the like terms, just like when you're solving the equation, the x squareds cancel out. And you've got a 3x cubed minus 12x that you're taking the integral of. And here, again, we have a negative x squared minus a negative x squared. Those cancel out. And here we have a 12x minus 3x cubed. By the way, since all we did was reverse the subtraction, it should end up being the same thing, just opposites. Okay? And then you guys can carry on from there. Are there any questions?
Could you not do, in this case, 2 times from like 0 to -2 of function?
That would only work if we knew that the two areas were exactly the same, okay? If you look here, if for whatever reason maybe we had some symmetry like with the sine and cosine one yesterday, those were periodic and we had some symmetry and whatnot, the two regions were identical, so we could have. But in this case here, okay, we don't know if this area here is equal to this area down here.
Yeah, and they don't
Okay.
look the same, so.
And yeah, they don't necessarily look the same, so. And by the way, again, remember if you have the graph, don't be afraid to estimate a little bit. You can always estimate just to get an idea of what it might be. You know, here's like a triangle, the base is 2, the height is 8. So that would be an area of 8 plus maybe another half up here, so that's maybe 8.5. And then over here, you know, this one might be a little more complicated, but like 1.5 by 6.
It's like almost
Yeah, that'd be 3 times 1.5, so that's about 4.5. And then
There's kind of a right triangle.
a 1.5, and it has a height of 8. So 4 times 1.5 would be about 6. So our answer should be roughly around 19. Okay? Now, again, you're not doing the whole problem this way, but it should be roughly around 19. And if you do this and you got something like 38 or whatever, then you probably lost a negative somewhere. That's going to be the biggest thing with these, is losing a negative somewhere in the process. So that little quick estimate can help you make sure you're in the right ballpark at least. Okay?
Sure, for both of them.
Okay, yeah, so we have 3x to the 4th over 4 minus 12x squared over 2. It'll still end up, yeah, so from -2 to 0, and then plus, again, 12x squared over 2, minus 3x to the 4th over 4, evaluated from 0 to 2. Yeah, so here it's going to be 0 minus, that -2 to the 4th is going to be a positive 16 over 4 is 4, so that's 12. Minus 24. Okay, so that's going to be a positive 12 plus, and then here, because they're even powers, I'll end up with the same thing. I'll have 12 minus 24. I'm sorry, no, not 12 minus 24, 24 minus 12. Minus 0. So 12 plus 12 is 24. What did we say it should be around?
19.
Around 19? That's decently close. Ours was a really rough estimate. You know, especially when we did these triangles, we were losing a lot there when we did those like that, you know? So that's a reasonable ballpark game. Okay? All right. So just a reminder of, if we're doing this, we take the top curve minus the bottom. One thing I do want to say, though, is we can also do this sideways. Okay? We can do this sideways. If we have our variables in terms of y, or our functions in terms of y, we actually can do the curve on the right minus the curve on the left and be integrating along the y-axis. Okay, now that's not something that we've necessarily done up to this point, but, you know, for example, if I have, you know, curves like this and maybe like this, I can integrate along the y-axis from intersection point. There would be my right-hand curve, and then if I subtract the left-hand, the integral of the left-hand one, that would get rid of that spot, and it would give me just the area between them, okay? So you can actually do this if your function's in terms of y, or sometimes it's just, it will be easier. You could do it that way, okay? Now, here's an example of that, okay? These are actually not functions, as you can see. Well, the one is a line, but the other one is not a function. It's, x equals 3 minus y squared. It's a horizontal parabola. And in this case, if I were doing the integral, doing it the way we have been doing it with vertical ones, we'd have to use this graph over here. But notice what we would end up having to do. There would actually be several things that we would have to do. First of all, we would have to get that x equals 3 minus y squared. X equals 3 minus y squared, we would have to represent as y equals. Okay? So we'd have y squared equals 3 minus x, and then y would be plus or minus radical 3 minus x. And we would need the plus or minus. Okay? Notice up here you have the positive radical 3 minus x, and here you have the negative radical 3 minus x. And you'll notice here, here's what makes it hard to do this. Okay? You'll notice we've identified the point where the line intersects this here at 2, 1. And that's because if you're looking at this vertically, right here, we are between the positive square root of 3 minus x and the negative square root of 3 minus x. So to find that, we would have to take the integral from 2 to 3 of radical 3 minus x minus the negative radical of 3 minus x. You see that? That's just that blue part. Okay? Then if you look at the rest of this area that we want over here, we are between the line and the negative radical 3 minus x, right? So for that part, I would have to go from this negative 1 over to 2. So the integral from negative 1 to 2 of the line y equals x minus 1. I'd have to rewrite this as y equals x minus 1. That's on top. And I'd have to subtract the bottom, the negative radical 3 minus x. And then I would have to add those two portions together.
So you're doing that blue part because there's no, line there, I guess?
Yeah, the line,
Stops at that.
we don't want this part all the way up to the line anymore. We only want it to go up to this curve. Okay, so we'd actually have to break it up into two separate parts. We'd have to rewrite the function in the first place. Or not function, we'd have to rewrite the relation as two separate functions so that we could do it vertically. Alright, that's the way we learned yesterday, or applying the method that we used yesterday. Okay? Today, however, if we think of it in terms of the horizontal, think of it in terms of right and left. As I go from the right to the left, I'm between the curve and the line, the whole region, right? And since I was given this as these relations in terms of y, okay, I can go ahead and do an integral with respect to y. Okay, now a couple things to watch here. I'm going to do one integral. What are the bounds going to be for this integral?
-2, 1, 3.
Yes. -2 and 1, because I'm going to be integrating with respect to y. So I have to go from the y value to the y value. Okay? So from -2 to 1. And then I do the right function, which is the curve. I keep saying function, relation. 3 minus y squared minus the left one. The one that's closer to the y-axis. So that's the line there, y plus 1. And you can see here, not only can I do it in just one integral, but also I'm not having to mess around with square roots and u substitution and all that stuff. Okay? So there are cases where you can look at it like this and it's much, much simpler to work with. Mm-hmm.
It's not always right minus left though, right? Because if there are any negative quadrants.
You would still do right minus left because you've got some double negatives going on there. It's kind of like if both of them were below the axis, you would still do top minus the bottom.
Okay, so not even mess with like left
Yeah.
minus right.
Yeah, you don't. It's all kind of built into that thing, and the negatives all cancel each other out. Okay, and remember too, if you happen to get it backwards and you get a negative answer,
Make
make it
it positive.
positive. Okay. Let's just finish this one out, just so we can get the hang of dealing with it with y's. We have the integral from -2 to 1 of 3 minus 1 is 2 minus y squared minus y dy. So 2y minus y cubed over 3 minus a y squared over 2 evaluated from -2 to 1. So when we plug in a 1, we get 2 minus a third minus a half. Minus, when we plug in a -2, we get a -4. Minus a -8/3. Minus a positive 4 over 2. So that's 2. Okay? So 1 minus 5/6, or 2 minus 5/6 is 1 1/6. Minus -6 plus 2 2/3 is going to be a -4 1/3. So it's now plus 4 1/3. And a third plus a sixth is a half. So this is 5 1/2. Okay. So, any questions about working sideways? Okay. All right. This down here is just a quick reminder that our integration is an accumulation process. This is why when we were taking, say, the integral of a velocity over the interval, that was giving us a total distance traveled on that interval of time. Okay? Here you see if we're going from -2 to -2, we have no area. So, but if we go from -2 to -1, we've now accumulated all of the area from here all the way over to the -1. And then if we go from -2 to 0, we've accumulated all of this area. Okay? Again, this is an accumulation process. Okay, if we've gone from -2 to 1, we've accumulated all of this area. And of course, if we want the entire thing, we've got to go all the way from -2 to +2. And we'll get this entire region. Okay? Alright, so just a reminder there that we are dealing with an accumulation process. Okay? And that still does apply even if we're working sideways on the y-axis too. Okay? Alright.